So the last two classes we were doing that big structure into internal loads. The thing looked like this. So there was a diagonal thing. And a horizontal thing. And on the horizontal one, there was a distributed load with a triangular shape and a maximum value of 400 newtons per meter. This angle is 30 degrees. This is 1 meter and this is 1 meter. And I labeled it, the horizontal one was member 1, the diagonal one was member 2, and then the joints I called A at the wall, B at the floor, and then C at the pulley. And we went through all those calculations. And we got that RA was equal to negative 3101.27, positive 1066.67. RB was 2101.27, and then for Y, 212.43. And F12 was 2101.27, negative 1376.17. Okay, so from that you can get the external loads on everything. And we did we pretty much covered the horizontal one. Once you get the external load, the external loads from the structures problem, we've done things like the horizontal member internal loads a ton of times. But today I just want to go through the diagonal member, make sure that it makes sense. You can check what you did and see if there's anything that went wrong with that. So first, I'm going to just draw out the member with all the external loads on it. So over here at the joint B, we have 2101.27 for X, 212.43 for Y. And then at the middle, this is the force negative F12. So this is negative 2101.27, 1376.17. And then at the end, we have a downward force of 1,000. And then we have a distributed load from the weight. It's uniform. And it has a downward value of 254.87 newtons per meter. Just writing the newtons per meter so we remember that's a distributed load. Okay, so what we want to do is to calculate the distributed loads, we want to be able to think of this as if it's lying horizontal, because that's what we're used to doing. What that really means is rotating the coordinate system so the x-axis is pointed along the member. So we need to come up with a rotation of the coordinate system that goes from this to this. And that's counterclockwise, so that's a positive 30 degrees about the z-axis. Okay, so our rotation matrix, capital Q, is cosine of 30, sine of 30, 0, negative sine of 30, cosine of 30, 0, 0, 0, 1. And now we just have to go with all these vectors. So 1, 2, 3, point force vectors, and then the distributed load vector. And left multiply all of those by, left multiply that matrix Q to each one of those. Really, the truth is there's no reason to do it for the 1,000 because whatever's on the right side, our cuts never get to it, you know what I mean? So we could do without that, but let's just be thorough. So, okay, the first one is Q times the vector 2101.27, 212.43, and then 0 for z, because this that's a 3 by 3 matrix. And you get 1925.97, negative 866.67, and then 0 for z. I'm just going through the one internal load that we didn't get to from that long class problem. And then now we're going to multiply that Q matrix times that second point force, which is negative 2101.27, positive 1376.17, 0 for z. And you get negative 1131.67, 2242.43, and 0 for z. And then the one that we really don't have to do, that downward force of 1,000, but I'm going to do it. 0 for x, negative 1,000 for y, 0 for z. And that comes out to be negative 500, negative 866, 0. And then last is the distributed load. So the rotation matrix times the vector 0, negative 254.87, 0. Is equal to negative 127.435, negative 220.724, 0. And this is the one that's newtons per meter. Okay, so now with these vectors, we've re-expressed this body with a coordinate system with the x-axis pointing along the member horizontally from left to right. Well, we could keep drawing everything at an angle and the coordinate system at an angle, but I'm just going to switch to drawing it now the way we're used to thinking about it, horizontal. But remember that what we've done is change the coordinate system. We haven't actually rotated the body, you know. So here's where we are going into the internal loads problem. So on the left, we have a force vector of 1925.97 and a y value of negative 866.67. At the midpoint, we have a force vector of negative 1131.67, y of 2242.43. And at the right end, we have a force vector of negative 500, negative 866. And last is the distributed loads. And we have two of these uniform distributed loads. You know, we're going to think of them as two different distributed loads, a horizontal one and a vertical one. The horizontal one is in the negative x direction. It's at 127. So I'm going to think of it as this way with a value of 127.435 newtons per meter. And then we have a vertical one of negative 220.724, so that's down magnitude of 220.724 newtons per meter. Okay, so that is the body with all its external loads on it. How many cuts are we going to take for this? There's a point force in the middle, so we have to do two cuts. So we have the two endpoints and the midpoint, so n is equal to 3, so we have two cuts. Okay, so cut 1. This whole thing has a length of 2.3094. So the first cut is going to go to the midpoint, so 0 to 1.1547. I don't know why I'm keeping so many decimal places, but I already did it, so I'm going to. Okay, so this is the first cut, so we know that whatever x is, we're not getting up to that point force in the middle. Word is spreading little by little about how great this lecture is. It's going to be full by the end. Okay, so at the left end, we have this force of 1925.97, negative 866.67. We haven't gotten to the other point force. There's the internal loads, T, V, and M. And then there's the distributed loads. I guess I'll draw those as distributed loads one more time. So we have the horizontal one going this way of 127.435 0.435. And we have the vertical one going down of 220.724. The horizontal one isn't going to contribute to the moment at all. So we don't, where the centroid is, that doesn't matter. But you can think of both of these as rectangular distributed loads. So to get the total point force, you multiply the length by the distributed load. And so if I draw this, now that we've chosen what part of the body we want to isolate, and we've chosen this thing with a length of x. Now we can replace those distributed loads with point forces. So we still have 1925.97, negative 866.67, and at the middle we have a point force going this way of 127.435x, and we have a downward point force of 220.724x. And then the internal loads. And so Newton's second law says 1925.97, negative 866.67, plus, I'll combine these into one vector. The x component is negative 127.435x. The y component is negative 220.724x. And then you have t negative v, and that's equal to zeros. And so t is equal to positive 127.435x, negative 1925.97. And v is equal to negative 220.724x minus 866.67. And now the moment equation. Our about point is at the left, so there's nothing from that force at the left. There's nothing from the horizontal distributed load. The 220, the vertical distributed load, has a moment arm of x over 2, and it's a clockwise rotation, and the force is 220.724x. And then you have plus the couple m, minus v with a moment arm of x, so minus vx is equal to 0. And so m is equal to vx plus this thing. So vx is negative 220.724x squared minus 866.67x, and then plus 110.7 0.362 x squared. And then you can simplify the x squareds. So m is equal to negative 110.362 x squared minus 866.67 x. You can do your checks now. dm dx is equal to v, so that's good. dv dx is equal to our downward distributed load. Well, is equal to negative our downward distributed load, so that's good. And then m should be 0 at the left endpoint, and v and t should be non-zero at the left endpoint. And you can see all that is true, so that's good. Any questions about that first cut? Okay, so now cut 2. And it goes from 1.1547 to 2.3094. So we're going all the way from the left, like always, to some x value that falls in this range, which means that we're definitely going to include this time this middle point force in our free body diagram. Okay. So on the left, we have this force of 1925.97, negative 866.67. Then at the second one that I've drawn already, we have a force of negative 1131.67, positive 2242.43. And we have the internal loads. And those distributed loads for the weight work out just like they did before, so I'm going to just skip the step of drawing them again as distributed loads. We still, at the midpoint of whatever our piece is, have a point force to the left of 127.435x and a downward force of 220.724x. So Newton's second law says 1925.97, negative 866.67, plus negative 127.435x, negative 220.724x, plus that second point force for this one, negative 1131.67, positive 2242.43, plus T negative V, is equal to zeros. And if you simplify this, you get T is equal to positive 127.435 X minus 794.3. And V is equal to negative 220.724X plus 1375.76. And now the moment equation. The only things that produce moments are the vertical forces. And not the one at the left. So we have the 220 thing, we have the 2242 thing, we have M, and we have V. So first we have negative X over 2 times 220.724X then plus 1.1547 times 2242.43 plus M minus Vx is equal to 0. And that all goes the same way as it did before. You get some cancellations and stuff, or some, like terms that combine. And you get M is equal to negative 110.362 X squared plus 1375.76 X minus 2589.33. And again, let's do the checks. dm dx is equal to V, so that works. Negative dv dx is 220.74, which is the downward distributed load. If I go back to this, it's the downward distributed load. So that one works. We should have, at the right endpoint, we should have non-zero T and V values, but 0 M value. And you can see that it's, well, the way you would see that is plug in X equals 2.3 whatever, and you would see that that's non-zero, non-zero, and this is 0. So everything works out. Well, if you plugged it in here, you would get it that it's equal to 0.9 or something, and you'd say, like, that's a pretty small bending moment. It's probably just round off error, and it is. Okay, so let's see what those look like as graphs. That's not where I want it. So for the internal tension, the maximum absolute value of the tension is right at the left end. Okay. There's no way without doing this problem we would have been able to predict that, but that's what it is. The maximum absolute value of the shear force is as you get close to the midpoint of that beam coming from the left side. Oh, no, it's not. It's at the right end. But then it's also like ramping up as you go from the left toward the midpoint. And then the bending moment, you can barely see the curvature of that. It's a quadratic function, but it's like, concave down on both of these two sides. So this comes to like a cusp, but we're at 0 at each of the two endpoints. And the biggest absolute value of the bending moment is at the midpoint. Any questions about that problem? The problems that I've given you on the daily assignments have all just been, they haven't included the weight. So it's just been point forces that you have to re-express in the new coordinate system. But I think in the weekly assignment, I gave you one like this, right? So anyways, hopefully this will sort of help with the weekly assignment. I did want to do one thing. I'm not going to do anything beyond this problem today in class, but I wanted to show, so I've talked about this just briefly a couple of times. We know that dmdx is equal to v, right? So we know that m is equal to the integral of v with respect to x somehow, And so, especially when you're in crazy things you're in the middle of internal load calculations with crazy triangular distributed loads and stuff all over, you're like, I really wish there was an easier way. And you maybe suspect that the easier way would be to just integrate the shear force function, But the question is, what do you do with the end conditions? Because when you integrate, you have a constant of integration, So what do you do to get that constant of integration? So let me just go through that, at least on one of these sides. We'll see how it feels after we finish the first side. And I'll show you how you could do that. I think what you'll kind of agree with is like, it really isn't that much better, Sometimes it's a little quicker, sometimes it's a little slower. For me, it's better to just do it the way we've been doing it and then use the derivative relationship as a check on your answer. But this is how you would go about it. Okay, so how would you use dmdx is equal to v to find the function m of x without using rotational Newton's second law? Okay. So let's go back to cut 1. And in cut 1, our shear force function was negative 220.724x plus 1375.76. And we know that the bending moment at x equals 0 is equal to well, I did mention it, but let's just go back and look at it. So when you, like as far as the checks, when you're done with your answers, what's the one about the bending moment at the endpoints? So yeah, in this case, it's equal to 0 at the endpoints. And the rule is it's equal to 0 if and only if there are no point couples at that endpoint. Okay. Point couples are either like a shown applied couple at that point, or more often it's a fixed joint that applies a couple to it, you know. So there's nothing like that. So there's no point couple at the left end. Okay, so we know that when x is equal to 0, the bending moment has to be equal to 0. Okay, so m of x is the integral of v of x with respect to x. And so that's the integral of negative 220.724x plus 1375.76. This is cut 1. Did I use the wrong one? Yes, thank you. Thank you. Minus 866. Okay. Minus 866.67 dx. Okay, so this function m of x is equal to negative 110.362 x squared minus 866.67 x plus some constant c. Okay, and now plug in x equals 0 and require that m is equal to 0. Okay, so that's what we know because there's no point couple there. So m for x equals 0 is 0 plus 0 plus c. And we're requiring that this is equal to 0. So we know that that constant c has to be 0. Okay, so now we can update our function. And we get our final function that says m as a function of x is equal to negative 110.362 x squared minus 866.67 x. And that's what we got before. Okay, that was really quick. So let's do the one on the right side. So now cut 2. So, so cut 2. What do we have for our function v? V of x for cut 2 is negative 220.724 x plus 1375.76. Integrate that and you get that m of x is equal to negative 110.362 x squared plus 1375.76 x plus c. Well, we know that when x is equal to 2.3094, m is equal to 0. We know that because that's another endpoint and there's no point couple at that point. Okay. So plug this value in for m, and you get m. I didn't bring, oh, did I? Oh, I do have a calculator. So we're just going to evaluate this function at 2.3094. And you get 2588.58 plus c, and we're requiring that that's equal to 0. And so c is equal to negative 2588.58 and so now update our function. And m is equal to negative 110.362 x squared plus 1375.76 x minus 2588.58. Well, this time, because of round off and stuff, it didn't come out exactly like what we had before, but it's less than 1 Newton meter, you know. So this is just round off error. Any questions about that? That's the length of the beam. So I just got that before I started from trigonometry. You had to know that before you did this problem because you had to know that the cut was half of that. Oh, and also you needed it to know what that distributed load was, because this is equal to the weight of the beam divided by its total length. But I guess I sort of just glossed over that. And I'm not going to do this, but, you know, why stop there? I mean, I guess calculating the shear force function usually isn't very complicated. So I guess that's why you would stop there. But remember that negative dV dx is also equal to Q. So once you come up with your distributed load function, you could just integrate twice, use the same boundary condition approach to come up with the bending moment, and never have to use Newton's laws. But it's sort of tedious doing the bending moments. And especially in a case like this where you have horizontal distributed loads, you'd have to relate the horizontal distributed load to the internal tension, which we haven't really talked about, but I mean, you could figure it out if you thought about it for 10 minutes or whatever, but you'd have to deal with that too. But you could do all this stuff with integration instead of Newton's laws. Anybody have any questions about that? Okay, that's it for today. Stay safe out there. You may want to just sleep here tonight. They have good couches in the student center.